Hello again, students. In the last video, we reached this part here where x double prime plus omega 0 square x equals to 0. This is our second order differential equation which governs the harmonic motion of the horizontal elastic pendulum, where omega 0 equals to k equals to radical k over m. Okay? The solution now of this differential equation is given in the form of, so it is given in this form, x equals to xm, which is the displacement or the shift of the spring. It's a constant, sine omega 0 t plus theta. Okay? Now, what is the meaning of each of these terms here? So, as we said, xm is the shift and it's a constant. Omega 0 is the angular frequency, time is t. Theta here is the phase. We call it the phase of the wave. And why are we talking about sine? Because it's a harmonic motion. Actually, the motion of the spring back and forth resembles the sine function. I'm gonna go back to this here. So let me show you. I'm gonna put this here. When the object is at equilibrium, x equals to 0. When the object is at maximum expansion, x equals to, let's say, plus xm. When it is into minimum compression, x equals to minus xm. So what we end up with is a sine function between plus xm and minus xm. Okay? Let me go back here. So the sine function, because the harmonic motion it starts from 0 to maximum, 0 again. Sorry, this is not how it's supposed to look like. So 0 to a maximum, 0, and then here, and so on and so forth. From 0 to the maximum is when it is maximally expanded, and then it reaches equilibrium here, maximum compression, equilibrium, maximum expansion, equilibrium, and so on. That's why it's a sine function, okay? So again, let me just write it in a better way. X equals to xm sine omega t plus theta. Okay, and what is theta exactly? Theta, if at time t equals to 0, the pendulum or the spring was not at xm, or was not at 0, I'm sorry, we have a phase. Okay, let me show you a bit. So if in our case here x of t equals to 0 was at xm, right? So we want that this thing would be 1 at x equals to 0, at t equals to 0. At t equals to 0. So sine omega 0 plus theta, I want it to be equals to 1. Okay, this is 0, so sine theta equals to 1. Theta should be pi over 2, because remember, this is the trigonometric circle. Cosine is down here, sine is up here. For theta equals to, let me use another color. For theta equals to 90, or pi over 2, sine would be equal to 1. Because remember, the trigonometric circle, the radius, it's a unity, so the radius equals to 1. So theta equals to pi over 2. That's the face, okay? The face, you can deduce it from the initial conditions, from the conditions of t equals to 0. Let me now erase what we wrote here, so we'll have a more organized page. Okay, let's continue now. Let's choose this color. So this here, x equals xm sine omega 0 t plus theta, is also called an equation of motion, but it is not in terms of x, it is in terms of time. So this is a time equation of motion, okay? And x and xm have the same unit, right? It's both a distance, both are a distance. And sorry, and what should we include as well? So xm is a positive constant because it shows it to be the shift to the positive direction, and x by itself, this x here, it is the abscissa along the x-axis. Okay, it's the abscissa along the x-axis as we saw here. So here is the x-axis, it's the abscissa as it moves, so here's x, 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 everything's x. Here x is positive, here x is negative. Let's go back. This x is the abscissa, xm is the shift, sine is the sine function because the oscillatory motion takes the sine wave shape, and this is the angular frequency, the time, and the phase, which is dependent on the initial conditions. Okay, so in our conditions, theta equals to pi over 2 because we started at xm, not at x equals to 0. Okay, and as we saw earlier, xm is the amplitude, let me delete here, is the amplitude of the oscillations. So if we draw, let us draw now the function, this function of x. Here, I'm sorry. So here we have the time t, and up we have the that's good, we have x. So here we have x with respect to time, or I'm sorry, x as function of time, and here we have the time itself. We start at xm, so our sine function won't start at 0, it will start at a maximum. That's a very high xm. Let's make it a bit lower. So here's xm, that's just this color. So you start by a maximum, it will fall down, a minimum, equilibrium, another maximum, a minimum. I'm sorry. Let's just make it better. And so on. So this is the function. We just drew the function. This is how the motion changes. So so the position x, it starts at xm. X starts decreasing, and then it reaches 0. Then it would go negative, and then it will increase the negative, and then it will start increasing again till the maximum, and so on. So if I want to draw it for you, we start at point xm, and then it starts decreasing, and here is the equilibrium position, and then it will move further to a compression, it will further compress. That's like how we explain the whole time equation of motion. Now let's study the characteristics of this simple harmonic oscillator. So we know that an oscillatory motion, it has a period and a frequency. We are going to call them a proper period and a proper frequency because we have this proper angular frequency, omega 0. It is radical k over m. K is a constant and m is a constant, making omega 0 a constant as well. Let's move to another page and try to calculate T0 and F0, or the period, proper period, and the proper frequency. First, we know that omega 0 equals to radical k over m, and it is called the angular frequency. The angular frequency, by definition, it is how many radians are covered in 1 second. So the unit would be radians per second. And we know that T0, the period, it is the time needed to complete one full cycle or oscillation. Now, in case of a circle, a full cycle would be from 0 to 2 pi. So a full cycle would be 2 pi radians, right? So a full cycle in radians, equals to 2 pi. So using this definition here and this definition here, we can say that and this oscillatory motion moves omega 0 radians in 1 second, and it moves 2 pi radians as well in the proper period T0. So how can we find T0? t0 equals to 2 pi times 1 over omega 0. So 2 pi over omega 0. t0 equals 2 pi over omega 0, and omega 0 is radical k over m. Then t0 equals to 2 pi. When it's just in the denominator, so we just flip it. It's equal to radical m over k. So we got our first characteristic of this oscillatory motion, which is, let's use another color. t0 equals to 2 pi radical m over k. Let's put it in a nice rectangle. It's a nice rectangle. Now we got the period t. The period t is in seconds. I'm sorry, this is not the way I should write it. So it is in seconds. Now, can we deduce the frequency? Of course we can. Let's use pink. The frequency, this is not pink, this is pink. The frequency, proper frequency equals to 1 over t0. That is 1 over 2 pi radical k. It is 1 over 2 pi and 1 over radical mk. This part here, we just flip it again. It is k over m, right? Let's go to another page. So f0 equals 1 over t0 equals to 1 over 2 pi radical m over k equals to 1 over 2 pi. We just flip it, it becomes k over m. K over m is omega 0, we already know that, so it is omega 0 over 2 pi. So f0 equals to omega 0 over 2 pi. Let's put it in a nice rectangle as well. Now we got the characteristics of this oscillatory motion. We have the frequency, the proper frequency, and we have the proper period. This is in hertz. Okay. Now, if we want to recap what we did, we first started by the conservation of mechanical energy between points A and B. Review the point A and point B. And from this, we got an equation. From this equation, it is a constant value equals to something in terms of V and X, right? We derive both sides. And we end up with a differential equation of the second order, or a second order differential equation. From this second order differential equation, we get omega 0, and we get x in terms of time, which is x equals to xm sine omega 0 t plus theta. We learned that omega 0 is the angular frequency, theta is the phase, xm is the maximum elongation, or it's the displacement, the shift. And from these values, we deduced what is f0 and what is t0. So by this, we completed this part of deriving the equation of motion. What I want you to do now is to open Pages. Let me go here. So your homework would be, of course, the homework. It would be first studying this part, studying how to, this part, or this video, let's say, how to derive the equation of motion. So basically, I want you to watch this video and then to try by yourselves to get the equation of motion again, okay? After that, I want you to open pages 64 and 65, read them because they show you the way of getting this equation of motion. And then on pages 65 and 66, I want you to solve. So I want you to solve application 1, application 4.1 and 4.2. Applications 4.1 and 4.2 already have a solution, but I want you to first solve it by yourselves and then check the solution and check if it was correct or not. Now, in case you have any questions about this video, part 1 or part 2, please don't hesitate to ask. You can send me your questions on WhatsApp, on Teams, or here you can comment on the video. Please take care of yourselves.